Good evening. Good evening. Today I will make some kind of review of our mathematical ideas for poets topics. So I have chosen for the first part a few words about arithmetic progression, about graphs, and about spanning trees. But first, as usual, history. So very often we discuss who are the most famous mathematicians. And of course, there's nothing like competition who is the most famous, but kind of historically, I have chosen maybe standard 5 most influential and famous mathematicians. I ordered them alphabetically. So there's Archimedes of Syracuse, you probably know a lot. However, maybe you don't know that he was not only a physicist, but great mathematician. Leonhard Euler, the essentially creator of graph theory. And then Johann Carl Friedrich Gauss, I will talk about him more. And Leibniz, he's kind of created graph theory as well. He have idea of new geometry, geometria situs. And finally, Isaac Newton, we know about him, about gravity, etc., but as well, creator of calculus, probably slightly before Leibniz, but independently of Leibniz. So I will talk a little about Gauss for a moment. With each of them, we should probably say a few words what they did, but let's concentrate on Gauss. So when Gauss was very young, he was from poor family of artisans in one of this principality close to Hanover, and then I would say that maybe it was lucky that there was compulsory schooling, probably under influence of Prussia. They wanted to have more educated soldiers, but in this principality when Gauss was, schooling became compulsory. So even this son of poor parents had school. School was not very modern, and all children of all ages were in class. Probably Gauss was then 7 years old. However, the story is told that maybe he was 7 years old. But he was kind of lucky, so I will tell the story. Let me erase, just keep on the Gauss. So once his teacher came to class, and anecdotes say that he wanted to read newspaper, so he asked children to solve the following problem. He thought problem is not difficult, but he thought that children will spend whole class counting. So the problem was to add numbers from 1 till 100. So 98 plus 99 plus 100. As I said, teacher thought that maybe children can solve this, but it will take them a lot of time. So to surprise of teacher, young Gauss immediately gave answer. Immediately gave teacher answer 50-50. So teacher was surprised by this, and in fact it has very happy ending. Teacher reported his able student to Prince, and then Prince took in his hand educating Gauss, and Gauss really, except short period in Napoleonic Wars, Gauss didn't have trouble with educating, being finally professor in Göttingen University. So how Gauss solved this problem kind of in memory immediately? He was saying something like this. Let's group this number first with the last, second with the second from the end, third from the third from the end, etc., etc. Always we are getting 101. Always 101. And now this 101 is how many times? It's not 100 times because we paired them. So it is 101 times 100 divided by 2. So if I didn't make a mistake in multiplication, and Gauss was not making mistakes, really he could multiply big numbers till old age, then you get 5050. So this was how Gauss did this. So how to generalize this method? So why this method works? Because we are going here by 1 up, and here down by 1. And we can try this pairing always, but what happens when you have, for example, adding number 1 plus 2 plus 3 plus 4 plus 5? Such numbers. We can try pairing, but because the number is odd, kind of 3 should be paired with itself. It may be awkward. Still, method works, but one has to do it more carefully. So today, first arithmetic progression is really sequence such that we move by the same step up. Not necessarily by one, by some step up. So I will illustrate this as kind of review, so I will illustrate this by one example. So this method will be almost like Gauss, except that instead of kind of pairing them, I will write the sequence backward. Then there is no problem that this tree has no neighbor, because I will write this 5 plus 4 plus 3 plus 2 plus 1. So that's so 3 is paired with 3. But here there's no problem. So let me erase this board and write some example very carefully. So let's consider our example. Find the sum. We call such sequence arithmetic progression because we'll be moving by the same step. So the sum of the following arithmetic progression. And I should state that arithmetic progression is kind of old word for sequence. So find the sum of arithmetic sequence. So where we start, let's say the sequence will be 27. Then I have to move by the same step up. So I'm choosing 5, 32. What is after 32? 37. Where to end? I think I have chosen will be 1 to 12 at the end. So what was before? 107, and before is 102. But remember, there are plenty of numbers in between. Okay, can you add quickly such numbers? So we'll use slightly modified method of Gauss, so nothing sophisticated. I should add that how to add arithmetic progression, here we move by 5, how to add arithmetic progression, already ancient Greeks knew, Archimedes, for example, knew. But this is kind of very naive way which let's do. So, how we start? It's useful to have notation. So let our sum be denoted by S. Notation is useful because we don't have to repeat the same phrase all the time. And now Gauss' method is to pair first with the last, etc. But I will do this by writing the sequence backward. So then we can write the same S as 112 plus 107 plus what was next? 102 plus plus what was 37 was next? 37 plus 32, and finally we started from 27. So, if you like to say something more sophisticated, you can do this because addition is commutative. We can add numbers in one order or another order. And now we pair them, so we add them. So, we have 2s, and this is crucial. We move by this 5 up, and here we move by this 5 down. So always will be the same. So what is this? 139, yeah? Again, 139. And again, 139. And of course, again and again, always 139. 139 plus 139. So problem is almost solved, but not totally. We have to know how many numbers we are adding. In the Gauss case, it was obvious. He was adding 100 numbers. But here it's not so obvious, because we start from 27, end with 112, jump by 5. So you have to find this. So this is equal. This is equal. 139 times the number of summands, how many times you are adding. So number of summands. So how to find number of summands in kind of naive but good way? So I would argue that when you have the sum, it is much easier to find number of steps in between. Not number of summands, but number of kind of how much we move. So this number I will call number of steps, how many times we move. So, and I argue number of summands is one more than number of steps. Obviously, because we have first step, first summand, last summand, and steps are only in between. So number of summands is equal number of steps plus 1. Why I'm claiming that it's much easier to find number of steps? It is much easier because what we are doing, we are moving from 27, which is the beginning, to the finish, which is 112. Kind of, let me write different color. Start, end. What distance I cover from start to end? Of course, this difference, 112 minus 27. 112 minus 27. So this is the distance I travel. And my step has length 2. Step of length 5, not 2. Of length 5, of course. Length 5. So this is distance I travel, 112 minus 27. And step has length 5. We have to divide this by 5. I hope you can see this. This is the number of steps. Number of steps. So this is very easy to compute. So what is this number? Number of steps, can I do this in memory? What is the difference? The difference is, let's do it slowly. First let's take out 20, so it is 92, and then say 85. So we have 85 divided by 5. What is 85 divided by 5? 50 by 5 is 10, and then you have 35 is 7, so it is 17. 17. But number of summands is number of steps plus 1. So number of summands is equal 17 plus 1 is equal 18. So we found number of summands. We can finish this calculation. I will do it here, but it's just small calculation. So this is equal 139 times 19. But it's not our sum. This is twice sum. So I don't like to erase. So let's move with maybe different color here. So we found that S is half of this. No, it was 18, not 19. 18, I don't. 19 would be bad because it will be not divisible by 2. 18, sorry. Let's say 18 and writing 19. Okay. So S is equal 139 times 18 divided by 2. So it is 139 times 9. And this one can compute. I think it is 1251. So our sum is 1251. So this method we can use for every arithmetic progression. I will stress one more. Let me just move by the given step here by 5. So in the next few minutes I will show one illustration from graphs. So let me erase this. Just remember that we can compute this using Gauss method. so just to recall, what is graph? Graph has vertices and edges. Every edge has either 2 endpoints in vertices or maybe loop 1. But I would like to make our application just in very specific graph. The specific graph is called KN, called complete graph on n vertices. It's from German, so it is K, not C. So complete graph on n vertices. Some people call this clique. So this is a very important family of graphs, but I would like to do very easy exercise when you can use arithmetic progression. So our question is, how many edges has this graph? But let's first make definition. The word complete is not precise. So what is complete graph of n vertices? Of course, Kn has n vertices. And every pair of vertices is connected by exactly one edge. And every vertices is connected by exactly one edge. Everything will be obvious if I show examples. Maybe I will start from the kind of the easiest example, K3. We have three vertices, and now we have to connect every pair of different vertices on an edge. So this will be just triangle. What is K4? K4, we have 3 here, maybe I put the 4 in between, and every 2 we have to connect. So we have this triangle, but now we have this. I will draw K5 when we're computing number of edges, but what is K2? K2. It has 2 vertices, and this should be connected by an edge, so it's just interval. But what is K1? K1, maybe K1 we have to think a little, but this one vertex, and nothing to connect. So K1 is the vertex, K2 interval, K3 triangle, K4 is a skeleton of tetrahedron, we can say it is this graph. So now, what is our task? Our task is to find number of edges of K, but not 4, but of general N. We have notation for this. I will just write edges of Kn. So I don't like to put absolute value, so it's just edges of Kn. So I need space, but I hope you remember definition. And let first examples, and then easily we'll devise general formula, but I would like it here use arithmetic progression. So we don't need definition, but we need pictures. So what we know from the picture? Number of edges of K1. There's no edge, it is 0. Number of edges of K2. It is interval, so 1. Number of edges of K3. Not yet that interesting is 3. Here is more interesting, we can easily count, there's 6. So number of edges of K4 is 6. Let's see more carefully what is the number of edges of K5. So what is K5? And this will be a hint. So K5 we can think is obtained from K4, we add one vertex and all connections. So we start from K4. And now we add one vertex, I will change color, and this should be connected to every vertex. Here you can make observation which is irrelevant to our counting, that this cannot be connected without crossing, but we'll just, here it is not important, there is not plane graph, it cannot be drawn on the plane. In fact, there's Kuratowski theorem which say exactly which graphs are planar and which are not, and K5 is one of the obstructions. So how we compute here number of edges? We see that we have number of edges which already were here, so number of edges of K4, plus we have new vertex connected with 4 vertices before. So here we get 10 number of edges of K5 is 10, as we can easily count, because there was 6 plus new 4, but really we would like to write that this is equal number of edges of K4 plus 4, because the previous graph had 4 edges, and these are called connections. This can be generalized. So let me erase this, and this can be generalized, and we are very close to the end. Because we can write by this experience the number of edges of Kn is equal to the number of edges of the smaller thing, Kn minus 1, plus connection. So here was n minus 1 vertices, so we have n minus 1 connections plus n minus 1. So we know that now Kn is n minus 1 plus the previous one. So we can go further. Now this is equal E of Kn minus 2 plus n minus 2 plus n minus 1. So we will see that if you continue this, we get arithmetic progression. We get 1 plus 2 plus n minus 1. Now we can use our method, or maybe quicker initial Gauss method. So if you add first to the last, second to the previous one, we get always n. Always n. Number of L is n minus 1 divided by 2. So this is our formula for the number of edges of complete graph of n vertices. So this is kind of, you can say, nice illustration of arithmetic progression. On the other hand, and this is known from Euler times, this reasoning, that you can do it differently. You can do this in one step. What is the reasoning? Euler-like reasoning. The Euler-like reasoning is like the following. Every vertex have n minus 1 edges, n minus 1. How many vertices you have? N. So you can think that number of edges is just n times n minus 1. But every edge, every stick has 2 ends. So it means that with this reasoning that this has n minus 1 companions and there's n vertices, we count every edge twice. So we have divided by 2. And you can say why we did arithmetic progression when we could have formula immediately. No, like in mathematics, when you have some problem, sometimes you can look at this problem from 2 different points of view. And then, because answer should be the same, you have some formula. So you can have different proof that this arithmetic progression adds to n times n minus 1 divided by 2. So in the second part of today's talk will be more about spanning trees. Thank you. We talked already about arithmetic progression. I was telling about graphs, and we are making some exercise with graph, in particular complete graph of k vertices. I will go to this complete graph, but what will be this in this part of the talk described, the spanning trees. Maybe before this I will tell some history. So famous physicist Gustav Robert Kirchhoff was the first person to carefully analyzing electrical networks, and in particular he defined something which he called complexity of the network. And today this complexity of network will be complexity of the graph under the name number of spanning trees. But of course first I have to define spanning trees. Then it is important work of Arthur Cayley, he computed how many spanning trees has complete graph of n vertices. Of course, without definition, we don't know, but at least there's this complete graph of n vertices. And finally, William Thomas Tutt, more contemporary 20th century mathematician, British-Canadian mathematician. He's maybe most famous that he found division of square into smaller unequal squares when he was still undergraduate student of chemistry. And then at the wartime, he was deciphering German codes pretty successfully. Then he did PhD and emigrated to Canada. He was working in Toronto and Waterloo. I will talk about his work later. I will talk about spanning tree. I will erase this, but before this, what is really tree? As we can expect, tree is something like this. What is special about such graph? First of all, it is in one piece, we say connected graph. Secondly, there is no closed paths. Kind of when you go, there's no other way than backtracking. So no cycles, no closed paths, and connected. So just before I will erase Blackboard, how we call the graph which is composed of many trees. It is not tree because it's not connected. How we call such a graph? Naturally, we call it a forest. But I will work mostly about trees. So next thing is spanning tree in concrete graph. These are abstract trees and now concrete graph. So I need space, so let's erase. So first verbally, we take graph G, and what is a spanning tree in graph G? It is subgraph, meaning it is made of pieces of G, which is tree, and what is meaning of spanning? That it contains every vertex of G. Let's write this. So we start a graph. Now T is a spanning tree in G if the following condition. I will write condition I mentioned. First, T is subgraph of G, meaning it's made of pieces of G. T is a subgraph of G. Secondly, as name suggests, it is a tree. T is a tree. Just to remind, tree is a graph which is connected in one piece. No cycles. So we cannot walk around coming back by different paths. The only way going somewhere is going backtracking. And finally, what is the meaning of the spanning? As I was saying, it means that T contains every vertex of G. Every vertex of G. So now I will draw some example. Let's draw the simplest example first. Usually we start from triangle. Maybe not the simplest graph, but simplest non-trivial graph. So let G be equal the triangle. How to draw all spanning trees of our triangle? We'll slowly go along definition. So spanning tree should contain every vertex. Then it should be connected and should be tree, so it should be connected and every vertex should be used. So there's not much choices, it's a piece of this triangle. So when we do this, we have to still connect this. So this will be nice tree. We should not add this because it will have cycle. What is other possible? We have these three vertices, and we can still start from this and then do this. And finally, we have these three vertices, and this should not be taken into account. So this is our set of all trees. So all spanning trees of G, we have three possibilities. Remember, just stress that spanning tree is different, it is sitting differently in this triangle. Because as abstract graph, you can say these are the same graphs, but they sit differently. The only other thing we will use is notation for the number of spanning trees, because this is this complexity of Kirchhoff, and we need notation for this. So for a moment, just a small space. Then I will erase this. So tau of G, so the Greek letter tau, is the number of spanning trees in G. The number of spanning trees in G. So what we computed that tau of our triangle is equal to 3. So before more examples, and I will start from easy examples, polygons, then I will consider polygons with double edge, and finally complete graphs K, N, and maybe some other families of graphs, but let me erase this. I will leave only the result for triangle. So the first exercise I will do is to see how many spanning trees has polygon. Remember, polygon Pn, it is n-gon. So triangle we did already. So what happens if n is equal to 2? What is 2-gon? 2-gon, as we can imagine, two vertices and kind of double edge. Number of spanning trees should be very easy. Let me draw them. It is spanning, so it has vertices. You can draw our edge either here, it is already 3, so you cannot add more, or it may be this. So 2-gon, that name for this is P2, has only 2 spanning trees. Tau of P2 is 2. What about 1-gon? 1-gon is really a loop. P1 is really the loop. Maybe that delicate thing. What are spanning trees of this? First of all, it should contain every vertex. But then, there's only choice either to use this edge, this loop, or don't use. If I don't use, that's okay. This is 3. Maybe very degenerate, there's no branches, but it is 3. On the other hand, if I take this, obviously there's path around, which is not backlacking, it's just cycle here. So it cannot be. So this is the only tree. The only spanning tree. So now tau of pi1 is equal to 1. So we see pattern, and it's kind of almost obvious, that number of spanning trees of Pn is n. But let's check this for square, and let's drawing for square. So G is equal to P4, meaning this is square. So maybe here philosophically, how to really get spanning trees from polygon? It is enough just to delete one edge. This is the reason that here will be 4 possibilities and generally n possibilities. But let's draw all of them slowly. Not to make mistake, first we draw all vertices and then connections. So let's start from the top, then we can add this or add this. I deleted this edge. And then we have, as we already observed, 4 possibilities. Now I will delete sides. These are our 4 spanning trees of square. So summarizing, tau fall is equal to fall. And experimentally, but reason is very easy, we have fact. Number of spanning trees of polygon is equal to n. So let's do this exercise slightly more difficult. Now I will consider a family of graphs when we double one edge. So let me erase this. So we already consider this graph. So let's remind, P prime of n is n-gon with one edge double. N-gon with one edge double. Again, I will start from triangle. So what happens when we have triangle and we double one edge? Doesn't matter which one, it's symmetric. Okay, so this is by our definition P3 prime. How many spanning trees it has? Let's draw all of them. Initially we don't know. So let's draw of them. How we draw? We have three vertices, so vertices should be all used because it's spanning. And now let's draw tree, so it connects this, so it is connected. Spanning tree. So one choice is like this. Let's try more. Now I have to use this, otherwise I will get the same. Let's say I take this. And then I get this. Or this. Now, instead of this upper head, I can take lower edge. And this too will be repeated. Lower edge, and this, and lower edge, and this. So clearly we can see that there's no more spanning trees. So what we got? That there are three spanning trees for this graph, or maybe I will write this tau of P prime 3 is equal to 5. Our goal is to find the rule for the number of spanning trees of Pn prime. So for sure we need much more of practice. Maybe what happened for P2 prime. So we know we have to start from 2-gon. But now we have to double one of them at one of these edges, which is kind of adding another edge. How many spanning trees has this graph? Of course, one edge is already spanning tree. So, spanning, so vertices, it may be this, it may be this, or it may be this. There is no choice. One edge is a tree. So we got that I will, saving space, I will write tau of P2 is equal to 3. You can try to find what is this for n equal 1. We know 1-gon was a loop, and now we have to double this loop. But we know that loops cannot be part of spanning tree because they are cycles. So the only spanning tree is a dot. So we got that tau of P1 prime is 1. So we have sequence 1, 3, 5. Maybe that's not enough to guess the answer. Let's draw at least one more square with double edge, maybe pentagon, but that will be a lot of drawing. So let's do P4 prime, which is square with double edge. Let's draw all spanning trees. Of course, if you try to follow formula, maybe especially we practiced arithmetic progression before, we can try to guess 1, 3, 5, what should be next? 7. we'll see whether really here we'll get 7. And if yes, then maybe we'll guess that there is general formula. So let's draw maybe all 7 spanning trees of our house. Okay. For vertices, let's start with something which has no roof. Okay. Now we have to operate with this roof. 1, 2, 3, 4. So let's say this part of the roof. And then we have to connect it to the rest. So maybe this. Or maybe this. Or maybe what is left. This was deleted. This was deleted. Now we delete this. And now we should repeat everything like this tree with lower part of the roof. So I will draw under, so that this will kind of give us pattern, trying to guess why our formula expect 1, 2, 3, 1, 3, 5, 7. Okay? So now we have this lower part. Otherwise I will repeat previous pictures and do it quickly. And the last one, spanning, so 4 of them, we decided this is this, and now should be like here. So it is more or less showing that we don't get twice the number of spanning trees of polygon, because this has no companion. So that's all, we got 7. So first of all, we found that tau of P for pi is equal to 7. Now maybe let's write 7 as we expect. It is twice 4 minus 1. This one has no companion. And now we can write formula similar to the polygon. Of course, we don't prove, but there is some strong suggestion that formula is 2n minus 1. So I will write this as fact, but of course it should be checked. But agree with all our examples. So fact tau of p n prime is equal to n minus 1. So I think I will consider only 2 more families of graphs. Maybe slightly more complicated, maybe 2 or maybe 3, because one will be kind of very similar to another. So now let's try something more. So let me erase p and prime. Now I will have 2 polygons and connect them by 1 vertex. So generally we have notation. If we take one graph and then another graph and connect them by 1 vertex, we write star. Just 2 graphs connected by vertex. You can say it is not well defined because we can connect here, here, here. It will happen that for number of spanning trees, there is no problem. So I will give example and then we'll try to guess the formula for this. So consider case of 2 polygons. Let's say triangle and square. We connect them by vertex, so really we are computing tau of triangle with square. Maybe I will use this picture because we have to have some fixed picture in mind. So we try to find all spanning trees of such graph. So to find all of them, we have to somehow organize them. And really this organization will show us the formula. Because what I will do, I will fix spanning tree here, and then put all possibilities here. And build the table of such spanning trees. So, first of all, we know that every vertex should be used. Okay. So I said choose for this triangle spanning tree. First, let's choose this. Then we could choose every spanning tree here. So, for example, this. Now I'll be trying to be quicker. So we have this piece I keep, and then I can take different one. 1, 2, 3. So kind of I deleted this edge, then I can delete this edge and the fold this one. So I would like to put everything here. So, which one was not yet deleted? I think this, and this. And finally I would like to draw it here. The first is deleted and this, and this. So you see, I'm trying to organize my spanning trees. I choose one spanning tree for the triangle and all possibles for square, and really they produce spanning tree. This is the hint what will be the result. But let me draw all of them. So now I have to take different spanning trees on the left. Let me choose, for example, this. And then on the other side, I will repeat just my picture so I can do it quickly. So I choose for triangle now this, and I'm repeating this. 1, 2, 3. And again, for the triangle I choose this, the same, but now I repeat this. And finally, I, of course, on the left side I'm using this pattern, but on the right side I follow this. So you see what I'm doing, choosing spanning tree on the left and trying all spanning trees on the right. There's one more possibility here, on the left. On the left, I can have something like this. And then I will repeat right side exactly as it is. This picture should be similar. 3. No, this triangle is not like this. 1, 2, 3. We take now on the left side this, and on the right side it will be this. And finally, and I repeat this pattern. Okay. Not only these are all spanning trees, and clearly we have 3 rows, 4 columns, so 12. This is 12 as we computed. But how I organize this tree suggests that we just take product of number of spanning trees here and spanning trees here. In fact, we can write this in full generality: spanning tree on the left, spanning tree on the right. Together they are giving spanning trees. I will not make any more examples, it's pretty long. So again, fact. Fact. Number of spanning trees of G1 connected by one vertex with G2 is equal tau of G1 times tau of G2. So this is one formula. Now we consider another family, slightly more complicated than this, kind of generalizing everything. This polygon and polygon with double edge, and we'll try to find the formula. So let's do this. I will do only one example and try to find formula. But test many more examples. To guess formula from one example you can. I would have to draw like 10 or more. But let's do this. So what is the idea? The idea is that we take 2 polygons, maybe I will say square and pentagon, but glue them along common edge. So this has name, so I will call this this concrete one will be P4, glue along edge with P, what I took, 5, 1, 2, 3, 4, 5, 6, yeah, P6. So square with hexagon and try to find formula for something like this. Clearly it cannot be very easy, but it's not difficult as it happened. Remember that this is a special case of doubling an edge, because if this is just 2 gone, then we have previous formula, so what you get should agree. So should I try to draw all of them here? Maybe there's too many of them. But I will try to kind of simplify this. And I make small, maybe jump. But I will stress this is the jump done by TAT. So this is a very special case of TAT formula. But how I'm computing this? I already have two special edge E. Spanning tree. So maybe let's put here that we glue them along E. Spanning tree now can be divided. Spanning trees which contain E and spanning trees which do not contain E. And let's try to divide the family of spanning trees for one another. So we try to compute number of spanning trees of our graph. Let's call this G, I don't like to repeat this. So pi number of spanning tree of G is equal. If our spanning tree is not containing E, I can take this E out of the graph and it will be okay. So this is tau of G minus E, meaning that I delete E. But it really for us means that spanning tree is not containing E. What is the second part? Second part should be number of spanning trees which contains E. This is usually denoted by G divided by E, because instead of having E as part of spanning tree, you can think of contract this. There's already this kind of jump. What really means contract? But just contract. E is not needed, E is always there, so we contract this. But using this, I don't have to draw. We see there's too many here the trees to draw them quickly. But I will know how many I have. Because when I delete this, I got polygon. I can count how many edges it has. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So there's 5 and 3, so it's 8 octagon. So I know what is 8. It will be 8. What about this? This is more interesting. However, you should believe that because E is the spanning tree, I can contract this. Contracting this is giving vertex. Well, E disappears, so this became triangle. Here was 6, but I'm taking out 1, I'm contracting 1, so it will be only pentagon. 2, 3, 4, 5. But my argument is now that just in the previous exercise, we said that it will be 3 times 5. So here I get 8 plus 3 times 5. What is that? 15 plus 8, 23. So this is giving some hint how to find the number of edges. It will be the number of polygon when E is deleted. So just n minus 1 here, n minus 1 here, and then I contract this, so again this times this. After some thinking, you get that, for example, here it is number of spanning trees of our graph, P4, P6 is equal to 4 times 6 minus 1. It's good to check whether I didn't make a mistake. 23, 23. And with small calculation, which we will not do, we can find that this is general formula. If I glue n-gon with n-gon, the number of spanning along edge, the number of spanning tree will be n times n minus 1. So let me write this as the fact, and then I will only shortly discuss complete graphs, but they require a lot of calculation, even to guess the formula. So see, this is just one example. I said it's difficult to guess formula, however, it is kind of motivation. Spanning trees without E and spanning trees with. And this method is TAT method. Mention about TAT. Okay. now this more complicated thing. What about tau of k n? This is too big really to make actual calculation quickly in the front of Blackboard. But for a small one we can do. So what is n equal 1? Complete graph of one vertex, so it's just one dot. So tau of k1 is 1. This is just spanning. Now for k2 it is just interval. So n equal to. So k2, two vertices connected, so it's just interval. This already 3, so we cannot do anything. So again, tau of k2 is equal to 1. For k3 already we computed tau of k3. What is k3? K3 is just triangle. We computed is equal to 3. What is tau of k4? Tau of k4, remember, 4 vertices, everything connected. This is reasonably good exercise. If I will do this, it will take me like 10 minutes. So I will not do this, but you can, with some patience, you can compute. The good start is to choose some edge and consider graphs which contain this edge and which don't contain. And after some, but not difficult, drawing, you get 8 with E and 8 without. So this is 16. So this is no big deal. But what about the sequence? 1, 1, 3, 16. Very difficult what is next. Usually, when you'd like to do C pattern, it is enough to compute tau of k5. But k5, we know, k5, innocent thing, but this is k4 with one additional vertex attached and many edges. So sometimes I play with this calculation, but practically it takes whole class. Usually, sometimes it takes me 1 hour or more than 1 hour I'm not even drawing all of them, I'm doing families. But it's families of trees. But if you like to repeat this calculation without any higher mathematics knowledge, what you will do is consider red vertex here and distinguish trees which has only 1 edge coming from this, we say degree 1, 2 edges coming from this, we say degree 2, 3 edges coming from this, and 4 edges. And each of them is a reasonable calculation. And then you add all together, and what you get, and this always, if you get correct result after all this long calculation, you are very happy, you get 125. Okay, maybe now it is possible to guess pattern. What is the pattern? 1, 1, that's nothing. But 3, nothing. 16 and 125. Now, usually there is somebody guessing this, even without knowledge. Because people say, what is this 125 number? It is clearly 5 to 3rd power. Maybe nothing special. But what about 6? 16. 16 you can say is 4 squared. Looks like pattern that we take number of vertices and raise to power 2 less. Let's see what happened with 3. Yeah, kind of in trivial way, it is 3 to power 1. But yes, it works. What about this? It is 2 to power 0. And we can say only by convention this is 1. But that's good. But what about this? This is just 1 to power minus 1. Whatever our convention, it is in fact 1. But it is a kind of small number. But here 3, 16 and 125 agree. And then it is famous theorem of Cayley. Even today it is not obvious theorem. You need some tools. But let me finish with this theorem. Cayley mentioned before. So this is 19th century famous theorem. Tau, this was already written here, tau of Kn is equal n to power n minus 2. You can try to prove this theorem, but without some setting, some knowledge, it is difficult. So, thank you. Thank you.